Okay, we're going to review over the materials that we were talking about prior to having a break with our classes. Moment of inertia is a property that talks about the strength of a material based on its orientation. It describes the stiffness of an object related to its shape or orientation. In general, if you have a higher moment of inertia, you have a material that doesn't bend as easily. So here you have an example of a diving platform which would have a high moment of inertia. If you try to bounce up and down on it, it doesn't bend very easily. A diving board, on the other hand, has a low moment of inertia. If you bounce up and down on it, this board will flex, it will bend, and illustrated or indicating that it has a low moment of inertia. Here you have two planks, one in the joist position and one in the plank position. Joist we also called vertical position, has a higher or taller part of the dimensions is a bigger number. Okay, the base is a smaller number. Here you have plank position, also called horizontal position, where the base is a longer number and the height is a smaller number. You can see the numbers, dimensions of both of these planks here on the bottom, and everything is the same except for the width for these are flipped and the height of these are flipped. If we calculate the moment of inertia, when we look at these, they look identical except for their orientation. Which one would bend more? Well, A would bend less than B because of its position. Okay, we could predict that just by looking at it, at the orientation of the wood in these two examples. B had a greater deformation because of the difference in the moment of inertia, and that was based on the orientation. So when we calculate the moment of inertia, we use this formula. Base times height cubed divided by 12. I stands for moment of inertia. Cubing this is really important. It shows that the height is the most important out of these two dimensions. Height is cubed, which means it becomes more important when we put it into this equation here. So calculating the moment of inertia of a beam, if we have this as 1.5 for the base and 5.5 for the height, put the numbers into the equation, 1.5 inches times 5.5 cubed, and we always divide by 12. That's putting these numbers here into this equation. We can do the calculations. We always want to cube the height first and then multiply it by the base. So when we do that, we multiply these two numbers right here. This is our number that we get, 249.5625 inches to the fourth, and we're going to divide that by 12 to get our answer. And when we do that, we get an answer of 21 inches to the fourth. So the moment of inertia for this beam in the vertical orientation, also called joist orientation, is 21. If we put that same beam into the plank position, or horizontal, also known as horizontal position, we're using the same equation to come up with the moment of inertia, base times height cubed divided by 12. So we put those numbers here. Now our base is 5.5, times our height is 1.5 cubed divided by 12. Again, we always want to make sure we cube this first, and then when we do that, we get these numbers. 3.375 times 5.5 divided by 12. Multiplying these gives us 18.5625 inches to the fourth divided by 12, gives us a moment of inertia for this beam in the plank position at 1.5. Remember previously we had calculated the moment of inertia of that same beam in the joist position as 21 compared to the second example or second calculations that we did. We came up with a number of 1.5. This number right here for a moment of inertia just tells you that it's more stiff. It's not going to bend as easily. It's a bigger number. 1.5, a much smaller number, bends, shown by this picture here, this illustration. It's bending a lot easier. So the moment of inertia, comparing those two numbers, will give you an indication of how easy the material will deform or bend or flex, all meaning pretty much the same thing. Here are some examples, if you remember this, of some composite shapes, and we're going to compare the shapes of the materials to a beam in its standard position. So here's the beam, and this is just a normal beam, nothing cut out of it, and here you have what we call an I-beam. Looks like the letter I. And you can see this material right here and right here have been cut out of this beam right here. So we have less material in the I-beam. If we can calculate it, and we'd come up with a moment of inertia for this beam as 10.67. The area of this material is 8 inches squared. We compare that to the area, 2.70 inches squared for the I-beam, and a moment of inertia of 6.08. If you look at these two numbers, you compare, 6.08 is a smaller number, obviously, than 10.67 when we're comparing the moment of inertia. So this is a more bendable material. It's not as stiff as the beam, but the beam uses more area. It uses more material, 8 inches squared compared to 2.7 inches squared. So the amount of material that is used in the I-beam is much less. In fact, as you see on the bottom here, the I-beam has 57% of the stiffness, so it's more flexible, but it only uses 44% of the material of the rectangular beam. So there's a trade-off. The regular beam is much stronger than the I-beam, but the I-beam wastes less material. So that's all part of a trade-off that you come to when you're looking at strength of materials and the cost of using one type of beam versus another type of a beam.